In our next example, we aren't going to be given the parameterization, but we are going to be given a function that that we're the graph of. So we're going to be computing a similar integral, so a path integral or an integral over a curve. But here we're not given the parameterization, so we have to come up with the parameterization. Okay. And when you have a graph like we're going to look at here, so let's just actually, before I even write a 1, let's just look at the graph of C. So in the plane, which we can view as R2 or we can view it as C, the complex numbers, we're looking from -1, let's maybe not use that, -1 to 2, and we're graphing y equals x cubed. So the cubed function from -1 to 2 looks something like this. Oops. Sorry, this kind of takes off. So this is our C. And when we're given that it's a graph of a function, actually the way in which we should walk along the graph is kind of determined. We usually choose to walk in the direction of increasing x values. So that's a convention. Okay, so we want to compute this integral, and in this case, what we do is we're kind of like automatically given the parameterization when it's the graph, although there's like a slight step we have to make. So what do points on the graph look like? They look like x, and then the value of y, and y is x cubed. So what we could do is we could say, we're not going to, but we could say set x of t to be t, and then y of t has to be what? Well, if the first guy is a t, the second guy has to be a t cubed. And what do the x values vary from? Well, they vary from -1 to 2, so t should vary from -1 to 2. So we could do that. We're not going to do that. It's okay to do that. It's just we already have a variable. It's x. We can just use the x that we're given. So all we're going to do is we're going to plug in y into this formula, and then we're going to integrate over x. And it's the same result as doing this other one. I shouldn't have crossed it out in red, but done is done. It's going to be the same result as doing this. And why? Because it's just relabeling. This process would have just relabeled x as t. So of course we're going to get the same result. All right, so let's do it. So all we're going to do here is we're going to replace all of the y's with x cubed. So the integral over c is going to be the integral from x is -1 to 2. X is going to stay the same. Y is going to become x cubed. So x squared. And then dy, if y is x cubed, dy is 3x squared dx. So that's going to be 3x squared dx. So let's see, what do we have here? We have an x to the 4th, and we have a 3x to the 4th for a total of 4x to the 4th dx's. That's a very easy integral to do. I hope we all agree. So that's 4/5 x to the 5th, evaluated from -1 to 2. So that's 4/5 2 to the 5th minus 4. Oops, don't need the parentheses there just yet. 4/5 -1 to the 5th. So this is what, 4, I'm going to factor out the 4/5. This is 4/5, oops, shoot, going too fast. 4/5 times 2 to the 5th. There's an odd number of negative signs, so that's going to become a +1. 2 to the 5th, I think, is 32. 32 plus 1 is 33. 4 times 33 is 132, I think. So, you'll have to check me. I'm pretty sure it's 132, though. All right, that's it. So here we weren't given the parameterization. We were given the graph. But if you're given a graph, so note well, if you're given the graph let me say it like this. If your curve is the graph of a function, just replace all the y's, or if it's a function of x, all the y's with the function of x, and just integrate like usual. if your curve is the graph of a function of y, you do the opposite. You replace all your x's with y's.